Hello, hello, am I audible?
Yes, ma'am.
No. Okay, okay, and my screen is visible too, right?
Yes, ma'am. Visible, ma'am.
Okay, okay. So, good afternoon, everyone. I welcome you to the sixth problem solving session of NPTEL course Graph Theory. So, let's begin. So, for, so from last few weeks we were doing matching. Today we'll be doing connectivity. So so first of all, few definitions. What do we mean? First is a definition of vertex cut. So what is a vertex cut? Vertex cut is basically some set of vertices such that when you remove those vertices, your graph become disconnected. So for example, in this first graph, if we consider this vertex C, if we remove this vertex C, the resultant graph will look like this. The like G minus C will look like this, and this is becoming disconnected. Therefore we can see that V dash C is a vertex cut with consisting of just one vertex. And similarly, if you look at this second graph, in this case, if you remove these two vertices, if we are just removing uh, so if we remove these two vertices ve and x, then also our resultant graph will look like something like this, uwy, and this graph is also becoming disconnected after removing vx. Therefore we see that this particular set is a vertex cut. So this is what we mean by a vertex cut. Now, next notion is of k connectedness. So what is k connected? It is a property of a graph. So we say that a graph G will be k connected if we remove any k minus 1 vertices. G remains connected. So basically, if we are saying k connectedness, so this is basically saying that if we pick any k minus 1 vertices out of that graph, and if we remove that graph, then the graph remains connected. So in this above example, you see, since this graph, this is G1, G1 is not one connected. Sorry, G1 is not two connected, because we are getting a vertex cut of size 1. So if G1 was 2 connected, then by definition it says that if we remove one vertex, then the graph should remain connected. But in this particular case, you see that if we are removing C, the graph is becoming disconnected. Therefore G1 cannot be 2 connected. But in this, so what about G2? What do you think? Is G2 2 connected?
Yes, ma'am.
uh
Yes, it is too connected.
okay. Why is it 2 connected?
Because if you remove only one vertex, the graph will not be disconnected.
Okay, so are you sure if we do it with any vertex, then the graph remain connected? uh, so what about v so does everyone think that G2 is 2 connected? So let's check
Yes,
it.
ma'am.
So let's check. So see, uh, if we are removing u, if we are just removing u, then the graph remains connected. That's true. But what about w? If I take my vertex set to be w, then is g minus w connected?
No. Yes, it is not too connected.
Huh. So therefore we see that G2 is also not 2 connected, because if we are saying G2 is 2 connected, then we have to check for every vertex. So if we, and similarly when you are looking for k connectedness, you have to so if you just don't check for one set of k vertices. So if G is k connected, if we pick any k vertices, and this property should hold for any k minus 1 vertices. So we see that in this G2 is not 2 connected. So if we look at the vertices U, X, V, other vertices than W, then the graph is remaining connected. But if we look at this particular vertex, just W, then the graph is becoming disconnected. Therefore, we see that G2 is not 2 connected. So now once we know what is K connectedness, we can define what is called vertex connectivity. So what is vertex connectivity? Vertex connectivity is the largest K for which G is K connected. So it is the largest K for which G is K connected. So in this in this graph, see in this graph the vertex, in both these graph the vertex connectivity will be 1, because vertex connectivity will be 1 because we see that both of them, G1 is not 2 connected and G2 is also not 2 connected. So for G1 and G2 our is vertex connectivity is K. So basically what we are saying is that vertex connectivity is K if G is K connected, but this K is the largest such K. So G should be K connected, but G should not be, G is not K plus 1 connected. Either this, so
And can you repeat? Can you repeat this?
which thing? Uh,
This
yeah.
last statement.
Yeah, so I am saying, so uh, so basically I'm saying that uh, vertex connectivity is basically, it is the largest K for which G is K connected. So and this K should, like, K is less than equal to N, uh, which is the number of vertices. So if G is K so basically if G is K, it is the largest K for which G is K connected. So basically G should be K connected and G is not K plus 1 connected. By largest we mean it is largest, right? Okay. Or the equivalent definition is minimum size of vertex cut as vertex connectivity also refers to as minimum size of vertex sets S such that G minus S become disconnected or has one vertex. So is the definition of vertex connectivity clear?
Yes, ma'am.
Yes. So, okay. So so first of all, let's find out vertex connectivity for some simple graph. So first example is complete graph on n vertices. So suppose let's we consider K3 for K3. So K3 complete graph on n vertices. So my first is K3. This yeah. So what do you think? What is the vertex? Is is this is K3 2 connected?
Yes.
Yes, ma'am.
Okay. Yes. Is K3 2 connected? Yes. So we see also see. So the definition definition is that it is the minimum size of vertex set such that G minus S become disconnected or has one vertex. So we see that K3 is 2 connected. That is, if we remove any one vertex, if we remove one vertex, then if we remove one vertex, this graph remains connected. So but then, oh, okay, so now we see that K3 is 2 connected and therefore we will see that connectivity is 2 because therefore connectivity is 2. because connectivity is always uh, sorry connect k sorry k3 is 2 connect, yeah, connect is k3 first of all, is k3 2 connected? Yes. Is k3 3 connected?
No, man.
Because if we, yeah, because if we
Because
remove,
if you remove two vertices, then it will be disconnected.
if because if we are removing two vertices, we are just left with one vertex.
One vertex.
So the connectivity definition is that we are looking for minimum set of vertices such that the graph become disconnected or the graph has just one vertex. So we
Hmm.
see so we see that if so we see that if we remove two vertices, then we are left with just one vertex. Therefore connectivity is 2. Now what about K4? What about K4? So this is K4. So first of what about K4? Do you think K4 2 connected?
No, it is not too connected.
Okay. Why is K4 not 2 connected?
Even if we remove two vertices, the graph will remain connected.
Yes. So okay, my voice is repeating. Is
So we need minimum three vertices to be removed to make the graph disconnected.
It is two connected, man.
So we need minimum 3. So graph is 2 connected, right? So 2 connected definition is that if we remove any g will be called 2 connected. If we remove one vertex, then the graph should remain connected. So if we are removing just one vertex, then this graph is remaining connected, right? Therefore
Yes.
this graph is 2 connected. You are right. The minimum number of vertices required to make this graph disconnected or just have one vertex is 3. So therefore connectivity is 3. So there are two definitions of connectivity. First definition is that it is the largest k for which g is k connected, and both are equivalent definition. Second is that either we tell what is the size of minimum number of vertices required to make this graph disconnected or just to have one vertex. So you see, so in K4, the minimum number of vertices required to make this graph disconnected, so this graph or to have one vertex is 3, because it is a complete graph. So if you are removing just one suppose if you are removing one vertex, all other vertices are attached to each other because it is a complete graph, so this graph can't become disconnected. And if you are removing two vertices, then also if you are removing two vertices, then also the other two vertices will have a common edge because it is a complete graph. Therefore you see at least three vertices are required. So is this fine? Why K4 is connectivity for K4? Why connectivity for K4 is 3? Is it fine?
Yes, ma'am.
Okay. So now can we generalize this? So so for
Ma'am,
K,
ma'am, in this case, ma'am, is K4 three connected? It can be three connected, no?
yeah, sorry,
K4, K4, it
yeah,
can be three connected, no?
yeah, yes, K4 is 3 connected, yes,
This K4 is three connected as well as two connected.
yes, yes, it is. So see, connectivity definition is so if a graph is 3 connected, then it is obviously 2 connected. So
Yeah.
so connectivity is basically it is the largest K for which G is K connected. So see, K4 is 2 connected, K4 is 3 connected. And since it has 4 vertices, we don't talk about 4 connectedness. Or because if it, since it has 4 vertices, if we remove 3 vertex, we are just left with 1 vertex. So we see that K4 is not 4 connected in that sense. K4 is not 4 connected. So K4, the largest K for which G is K connected is 3. Therefore connectivity is 3. And similarly, if you'll see for K5, this is K5, this is K5. So you will see that K5 is 2 connected, it is also 3 connected, it is also 4 connected. uh, it is 2 connected, 3 connected, 4 connected, but it since it has 5, but it is not 5 connected. So 4 is the largest 4 is the largest K for which this G is K connected, therefore connectivity is 4. Is this clear? The definition of K connectedness and connectivity.
Yes, ma'am.
Is it clear for everybody? If you have
Yes,
doubt,
ma'am.
we can I can repeat. Okay.
Madam, madam, it
Yes.
means
Yes.
three connected graph is uh, has connectivity three,
No, no. Uh, 3 connected graph does not
right?
have connectivity 3. Connectivity is
In case of
basically,
K4, so here in case of K4,
yes.
uh, the connectivity is three as well as it is three connected.
No, no. Yeah, in K4 it is it is 3 connected as well as connectivity is 3 because
Uh,
3 is the largest K for which it is K connected. But in K5 you see K5 is 3 connected, but K5 is also 4 connected. So here the largest K for which K5 is K connected is 4. Therefore connectivity is 4. Okay, is it fine?
Ma'am, one doubt, ma'am.
Yes,
in
yes,
the
yes. Yeah,
What about every graph with connectivity 5 is 5 connected? Is it true or false?
yeah. If a okay, we'll see that. So if suppose you are saying G has connectivity 5, right?
Yes, ma'am.
So your question is G5 connected, right?
Yes.
is G5 connected? Is G5 connected? Is G5 connected?
Huh? Yeah. What are you saying?
Yes, yes.
So see, G has connectivity 5. So connectivity means that maximum of K such that G is K connected, right? So G has connectivity 5. That means 5 is the maximum of that. So therefore G has connectivity 5. That means that G is 2, 3, 4, 5. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4, 5 connected, but G is not 6 connected. 1, 2, 3, 4,
Okay, ma'am. Thank you.
Okay. So the answer to this is yes.
Okay, ma'am. Thank you.
Yeah. So this is so there's a difference between K connectedness and connectivity. So this is the precise difference. So now let's compute connectivity for some bipartite graphs. For some complete bipartite graph. So first of all, let's take K23. Yes. So first question is the K23. So the size of vertex set is 6. So first question is G2 connected?
Yes.
Is G2 connected?
Yes, ma'am.
Yes. Okay. Why? So if we remove any one we see that if we remove any one vertex, this graph is remaining connected. Why? So because if we are removing this one vertex, so this is a complete bipartite graph. So if we remove just one vertex from here, if we remove just one vertex from here, so all the remaining vertices, so this is a complete graph, so there will be edges going out, so from the so so we have, so the graph will be this, and since it is a complete graph, it is attached to every edge in the other bipartition. So we see that if we are just removing one vertex, this graph is remaining two connected, therefore this graph is two connected. Now is G3 connected? What do you think? Is G3 connected? That means you have to check removal of two vertices should not make this graph disconnected.
This depends on the choices of vertices, ma'am.
Huh, but for connectedness, it should happen. Sorry, uh, uh, can you mute yourself? I'm hearing echo for like, hello. Yeah, so I'm saying, so see, for showing K connectedness, you have to check for every K minus 1 vertices. So if you want to say that G is 3 connected, you have to show that removal of any two vertices should not make, if removal of any two vertices is not making this graph disconnected, then this graph is 3 connected. So what do you think?
Yes, three connected.
Are you sure?
Are you sure? Any no, if we remove that one from other
I
side
I'm
to
I'll name them. Yeah.
if we remove D and E, this then becomes disconnected.
Yes.
Others, other pair it won't work.
Oh, so it cannot be three connected, na? So we have to check removal of any two vertices. So basically, if you it's, so you are getting a pair DE, right? So if you consider your S to be DE, then G minus S is becoming disconnected, right? So it cannot be three connected. By any two vertices, I mean that we you if we pick any two vertices, basically this, if this graph is becoming disconnected for any one pair of vertices also, then also this graph is not three connected. So if you are getting two vertices whose removal will make this graph disconnected, then this graph cannot be three connected.
Okay, ma'am.
So therefore, is it, this graph is not three connected? Is it? Is,
Yes, got it.
so what is the connectivity for this graph?
Two. Connectivity is two.
Yes, connectivity is true because we need to look for the maximum one. So it is two connected, but it is not three connected. Therefore, connectivity is two. Now let's do just one more example to see if the definition is clear. So let's say K
I mean,
K4.
what is the relation between connectivity and connectedness?
So this is the relation, right? Connectivity is maximum. It is the maximum K for which G is K connected. So 2 is the maximum. 2 is the maximum K. 2 G is 2 connected, and 2 is maximum such number. Therefore, G is 2 connectivity is 2. This is the relation. Is that clear? Is it okay?
Here, three connected graph
Hmm.
has connectivity two,
This graph is
right?
not. Is this graph is not 3 connected?
Uh, okay.
But yeah, if a graph is, so if a graph is 3 connected, uh,
Then connectivity cannot be equal to two.
yes. So basically, if G is K connected, then connectivity is greater than equal to K. If G is K connective, G connectivity is greater than equal to K, because connectivity is maximum such K. Now if we consider this graph K4 3, okay, so
It means
yeah.
my for five connected graph,
Hmm.
the connectivity should be five or more than five,
Yes, yes.
isn't it? Okay.
Yes, because see, if G is, so do you see that if G is K connected, then G will, if G is K connected, then G is also K minus 1 connected. That is fine, right?
Okay.
So, and connectivity is basically maximum K for which connectivity is maximum K for which G is K connected. So, if G is K connected, then the connectivity should be greater than equal to K,
Okay.
because maximum of such will be K or greater than K. So, now if you are looking at K4 3, suppose. So, first of all, is G2 connected? Is G2 connected?
Yes. G is two connected.
G is 2 connected. So you see, if we G is 2 connected, yes, because if we remove for checking 2 connectedness is that we have to see that if we are removing just if we are removing one vertex, this graph should remain connected. So if we'll remove one vertex, then there will be some sets, and this is complete graph. So so every vertex in B is connected to every vertex in A. So if we are removing just one vertex, this graph is remaining connected. Therefore, we see that this G is 2 connected. What about is this G 3 connected?
Yes. Even if you remove two vertices,
Hmm.
graph will remain connected.
Yes. And we can see, yes, this is this is true, because if we are removing two vertices, so basically if we are removing two vertices, then we have at least one vertex which is, so we are removing two vertices, so we have at least one vertex which is in A and at least one vertex which is in B, and all the vertices in A are connected to all the vertices in B. So whatever remaining vertices we have, we'll have some. We'll see that all of those vertices will be lying in the same component. If we are just remove if there is one if we are removing just two vertices, right? So what can happen? So why is G3 connected? Let's show this. So suppose we are remove so we have to check that G is 3 connected. We have to check that if we remove any two vertices, this graph should remain connected. So first case 1 is my V1 and V2 is belonging to A. Both V1 and V2 are in A. So if both V1 and V2 are in A, suppose I am removing E and F. Suppose I am removing EF. So I see this remaining vertex G is connected to A, B, C, D. This G is connected to A, B, C, D. So the graph that we are left with is like this. So we see that this graph is remaining connected. Now case 2 is if V1, V2 is contained in B. Suppose we are removing two vertices from B. Now if we remove two vertices from B, our graph will be like this. So we'll have two vertices here and three vertices here. And this graph will also remain connected, because then we are left with graph of type this. And case 3 is one vertex is in A and other vertex is in B. Then we are left with three vertices here and two vertices here, and all the vertices are attached to these vertices. So so we see that so we see that this remains connected after removing this also. So we have now there, so we have seen from all both these cases, so from we have seen from wait, this is this and this edge also and this. So now we have seen, like, now we have seen that if we remove any two vertices, this graph is remaining, this graph is remaining connected. Therefore this graph is 3 connected. But what about 4? Is G4 connected? What do you think? Is G4 connected? So first of all, did everyone understand why G is 2 connected and 3 connected? Is it clear or should I repeat?
No, it is clear.
Clear, ma'am.
So what about what do you think? Is G4 connect? Now so see, we are trying to find the connectivity of this graph. So we know G is 2 connected, we know G is 3 connected. So what is G4 connected? So basically to check G4 connected, you have to show that if we remove 3 vertices, we'll have to check for all all collection of 3 vertices, and if we are removing those 3 vertices, this graph should remain connected. So if you can find 3 vertices whose removal will make this graph disconnected, then this graph is not 4 connected. So do you think the G is G4 that G is 4 connected?
Yes, it is. It is 4 connected
Why?
because because if you remove the vertices A, B, and C, the final graph is connected.
Yes, but see, that is happening just for these three vertices. But to check connectedness, you have to check for all collection of three
All
vertices,
others. Okay, okay.
all others also.
All others are.
N- so
Uh,
none of the
if you remove, then if you remove E, F, and A, then it becomes disconnected.
yes. So if we take S as E F G,
E, F, G.
E F
Then
G,
graph becomes
then this graph
disconnected.
become disconnected. So basically, uh, minimum number of vertices required. So our connectivity is coming out to be 3. Hence G is not 4 connected. G is 2 connected, G is 3 connected, but G is not 4 connected. So for maximum K for which G is K connected is 3. Therefore connectivity is 3. And this matches with our other definition also. That is minimum number of vertices required to make this graph disconnected is 3. So is this clear? Is this clear? Why connectivity of this graph is 3? Okay. Yes, yes.
Here in this case,
Yeah.
connectivity is three, and it is uh, three connected, right?
Yes, yes. Yes. So see, if connect so this
It
we
means the
checked.
number remains the same, no?
Yes, yes. See, this somebody asked this question also. So if a graph has connectivity, so this is always true that G has connectivity K. If G has connectivity K, then G is K
It
connected.
is K connected.
This is always true. So if connectivity is 3, then G has to be 3 connected.
Yes.
But we have
If the
connectivity is additional thing that it is K connected, but it is not K plus 1 connected.
yeah,
Okay. So we see that G is 3 connected, but G is not 4 connected. Therefore, maximum K for which G is K connected is 3. Is is it clear?
yes.
Yes, ma'am.
Okay.
It means if the graph is
Yeah.
K connected,
Yes.
then its connectivity is K
Connectivity is greater than equal to K.
greater than K. Okay.
Yes. G G has connectivity K, then G is K connected, not K plus. And if G is K connected, G has connectivity, then G has connectivity greater than equal to K. Okay. Also, this is one definition. The other definition is also, so this is one definition. Another equivalent definition was that connectivity, that minimum number of vertices required to make this graph disconnected. So you see in this, so we are getting 3. Okay. So now next. So now once we have done vertex connectivity, next thing is edge connectivity. So first of all is, what is an edge cut? Edge cut, it is the set of edges of cut, the cut of form this whose removal disconnects the graph. So vertex cut was set of vertices whose removal was disconnecting the graph. Edge cut is the set of edges whose removal will disconnect the graph. And if we are writing something like square bracket S bar, so here we means that all the edges whose one endpoint lie in S and other in S complement. So now suppose this is our graph G. So if we take this edge CD, if we remove this edge CD, this graph is becoming disconnected. Therefore our edge cut here is CD. And edge connectivity, and similar like vertex connectivity, edge connectivity is size of smallest edge cut. And now we had, when we were saying k connectedness, we were referring to vertex connectivity. And similarly there's a notion of k edge connectedness, which is that k vertex connectivity was that if we remove any k minus 1 vertices, then the graph should remain connected. K edge connectedness is that if we remove any k minus 1 edges, then the graph should remain connected. And we have a nice relation between edge connectivity, vertex connectivity, and the least degree. So so we have that this was done in the lecture, that vertex connectivity is always less than equal to edge connectivity, which is less than equal to the minimum degree, which is less than equal to the minimum degree. Okay, so now let's do some questions. So we have done connectivity, so this is just recalling. So now what we had a long discussion about connectedness and connectivity. So this should be a trivial question now. So now tell me which of them is true. One of them, every 4 connected graph has connectivity 4, or every graph with connectivity 4 is 4 connected. Which of this statement is true?
B. Statement B.
B, man.
Statement B is true.
Yes, statement B is true and statement A is false. So why statement A is false?
All five connected, you know,
Yeah, huh?
every four connected graph connectivity four need not be, because the four connected graph may also have five connected.
Yes,
It can also be five connected.
yes, yes, yes. Also, you are right. Or more, if you consider if you consider case 6, if you consider case 6, you see that this graph is 4 connected but has connectivity 5. This we have discussed in the previous only, that for kn connectivity is n minus 1. So we see so case 6 is 4 connectivity. So we see that first statement is false and second is true. Okay, so next question. Now first thing is, first we have to show that G is 2 edge connected if and only if every edge lies on a cycle. So how do we prove that? First of all, what do we mean by 2 edge connectedness?
Which connected means removing of one edge do not disconnect the graph.
Yes, G is 2 edge connected. That means that removal of any one edge does not disconnect the graph. So now you need to show this. Now we know what is 2 edge connectivity. Now we know what is 2 edge connectivity. So now suppose G is 2 connected. Why do you think every edge lies on a cycle? So we are given that G is 2 connected. Now G is 2 connected. Let E be an edge of G. Let E equal to UV be an edge of G. Now why why there should it should lie on a cycle? So G is 2 connected. Let E be an edge of G. So we have to show that every edge lies on a cycle. So we are assuming that G is 2 edge connected, and we have to show that every edge lies on a cycle. So my assume G is 2 connected. Now we have to show that every edge lies on a cycle, so we pick some edge E. Let E be an edge of G. So if E is an edge of G, and since G is 2 connected, then that means that G minus, since G is 2 edge connected, that means G minus this edge E is connected, right? Because that is the definition, by definition. Now if G minus E is connected, that means there exists a UV path in G minus E. Now can you see that why E lies on a cycle? So the question was, first of all we are assuming that G is 2 edge connected, and we are showing that every edge of G should lie on some cycle. So we picked some edge E UV. Now we have to show that this is lying on some cycle of G. Now since G is 2 edge connected, we know that G minus E is connected. Now if G minus E is connected, therefore there exists a UV path in G minus E. Now we have that UV is an edge in G. UV is an edge in G E. So G is some graph and UV is some edge. And after removing this edge, this graph is remaining connected. So that means if this graph is remaining connected, that means there should be a path between U and V. Now can you see a cycle in G? Do you think that, so there exists a UV path, say U, V1, V2, Vk, V in G minus E. So now do we get a path? Now do we get a cycle containing edge UV? So isn't this isn't this up cycle? So if we go along this path and then this edge, this will give us a cycle, right? So basically U, V1, V2, Vk, V, and then U. This is a cycle, right? Is a cycle containing E. So is first implication clear to everybody that if G is 2 edge connected, then every edge should lie on a cycle. So this was forward implication. We were showing that, so we were assuming that G is 2 edge connected, and then we were showing that every edge is lying on a cycle. So is this first implication fine for everybody? Or is there any doubt?
No.
Now reverse implication. Suppose we are supposing that every edge lies on a cycle. So if and only if every edge lies on a cycle, yeah, G is two edge connected if and only if G is connected and every edge lies on a cycle. So now suppose every edge lies on a cycle and suppose G is connected. Now we have to show that G is two edge connected. To show G is two edge connected. So what do we need to show to show that G is two edge connected? So the question is this. So we have to show that G is two edge connected if and only if G is connected and every edge lies on a cycle. So we have shown one way around. That is, if G is two edge connected, then G is connected and every edge lies on a cycle. So we have shown this. Now we have to show the reverse implication. That is, suppose G is connected and that we are given that every edge is lying on a cycle. We have to show that G is two edge connected.
So similar, no? If you
Yes.
remove one edge, there will be a path between.
Yeah. Same. Yes. Right. So G is two edge connected if we are removing G minus E. And now E lies on a cycle. So we are getting a path. G minus E where E is equal to UV. Now E lies on a cycle. Therefore, there is a UV path. And all other and there is no change between other paths. Therefore, G is two edge connected. Good. So now we have shown this. Two edge connectedness is equivalent to saying that G is connected and every edge lies on a cycle. So now we have true false. First is that every two edge connected graph is two connected. So what do you think? Is it true or false?
False. False moment.
False, man.
Okay. Why? Yes. So,
So if you remove one edge, then graph doesn't disconnect.
yes. So every two edge connected graph is two connected. This is false because if we consider something like this. So you see that every edge is lying on some cycle. Therefore, this graph is two edge connected. But this is not two connected because if we remove this vertex, this graph is becoming disconnected. Right?
Yes.
So,
Yes.
but is this true that every two connected graph is two edge connected?
Yes.
Yes.
Yes, ma'am.
Okay, now you have to tell why. Suppose so you are saying that if G is two connected,
But not to edge connected.
if G is two connected, then G is two edge connected. Why this is true?
G is two connected means removal of a vertex does not disconnect the graph.
Yes.
If we remove one vertex, we will at least delete two edges, I think, or at least a edge.
One
The
edge.
graph will remain connected.
Yes. Yes. Yes, yes, that is fine. So basically you have to show that uh, removal of an edge does not make this graph disconnected. So basically, if suppose we start with, let e is equal to uv, so we have to show that g minus uv is connected. Or you can also see, so we have this inequality also, that kg is less than equal to k dash g, right? So if g is 2 connected, if g is 2 connected, that means kg is greater than equal to 2, right? This implies that k dash g will also be greater than equal to 2. Therefore, edge connectivity is either 2 or greater than 2. Therefore, we see that G is also 2 edge connected. So, we can generalize this basically, that if G is K connected, then G is also K edge connected. Due to this nice relation that we have, that edge vertex connectivity is always less than equal to edge connectivity. So if G is K connected, that means Kg is greater than equal to K. But Kg is less than equal to K dash G, which is edge connectivity. Therefore, we see that K dash G will be greater than equal to K. Therefore, uh, uh, and if edge connectivity is greater than equal to K, that means G is K edge connected. So is this clear?
Yeah.
Okay. Uh, Now you are given this particular graph. Now first you
In
have,
K, hello, madam. In
yes,
KH connectivity, in KH connected graph,
yes,
uh, then K is greater than one, or K can be equal to one.
uh, so, so
What is the value of K? If K is greater than one, or K is equal to one in KH connection connected graph.
what is your question? If a graph is K connected,
Then what is K? K is greater than one, or K is greater than or equal to one.
greater than or equal to 1.
Okay.
So see, one connectedness just means that G is connected. So like you can one connected one connected means G is connected. So what will be the definition of one connected? That removal of zero vertices should make removal of zero vertices should
One edge connected graph. Is there one edge connected graph?
Path is a one edge
one edge
connected.
connected is also similarly one connected only.
One edge
Huh.
one edge connected graph is there.
One by one edge, yeah, so one edge connected graph will be the graph with connectivity 1, basically the graph with a so this will be one edge, so this graph is one edge connected, so this graph is not two edge connected, right? It is not two edge connected, right? But it is one
Yes.
edge connected. One By one edge connectivity, it also we mean that removal of zero edges should make the should not affect the connectedness of graph. So basically, one edge connected is also say one edge connected or one connect. By one edge connected or one connected, we just mean that graph is connected. So this graph is one edge connected. So basically, all connected graphs are one connected and one edge connected. Was this your question?
Okay, I got it.
Okay. So now we have this graph. This now, what is vertex connectivity of this graph? So basically, minimum number of vertices, minimum number of vertices that make this graph disconnected. So what do you think this what is the vertex connectivity of this graph? So first of all, is G 2 connected?
Yes.
Okay. So what is the connectivity of this graph? Is G2 connected? Yes. So
Yes.
basically, removing any one vertex should not affect the connectivity of this graph. Or so so we see or basically or basically we can see that every every edge every edge in this graph, every edge in this graph is lying on some cycle. Therefore this is this G, is G 2 edge connected. So we can from our previous exercise we can see that every edge lies on a cycle. Therefore this graph is 2 edge connected, and if this graph is 2 edge connected, this graph is 2 connected also. Or you so we have to find the connectivity. First of all, we are trying to find the vertex connectivity. So this graph is 2 connected. That means removing one vertex is not making this graph disconnected. But what about removing two vertices? Is G3 connected?
Yes, ma'am.
Yes. Once we remove the connection with
Look carefully
hmm,
to show that G is 3. So basically you are saying that uh, no pair of vertices, removing no pair of vertices not making this graph disconnected. So I'm telling you that this graph is not 3 connected. So now can you give me two vertices which is making this graph disconnected?
D and J, ma'am.
Okay. So if we remove D and J, let's see. Uh if you are removing D and J, do you think this graph is becoming disconnected then? See, E is a okay. If we are removing D and J, so the graph is this. So basically, if we are removing D and J, we are saying that is this. So okay. So does everybody agree that DJ is a vertex cut? That removal of DJ, G minus DJ is disconnected. right? So if we look at, so if we remove, see, he's right. So if we remove these dj, what is the result, like after removal, what is the graph that we are left with? So we are left with a b c e in one component, and g f h i in the other component. So this graph is becoming disconnected, right? So we see that G is not 3 connected. So now what is the connectivity of G? What is the connectivity of G then? If G is 2 and connected but G is not 3 connected, so what is the connectivity of G? Isn't connectivity 2 then? Because, so is it fine with everyone why connective vertex connectivity is 2 for this graph?
Yes, we
Huh?
yes.
Yes.
Vertex connectivity is 2.
Okay. Now what about edge connectivity? What is the edge connectivity for this graph? So we have already seen that G is two edge connected because every edge, you can see every edge is lying on some cycle. And from our previous exercise, if every edge lies on a cycle and if G is a connected graph, then G is two edge connected. What about the three edge connected? Is G three edge connected?
No, it is not 2 edge, 3 edge connected.
Why? What two edge?
Because because on removal of 2 edge, the graph we cannot disconnect.
Huh? Can you repeat what you're saying?
By removing 2 edges,
Hmm.
the graph cannot be disconnected. This cannot be disconnected. So it is 3 edge connected.
It is, so you are saying it is three edge connected.
Yes, it is 3 edge connected.
Okay. So it is three edge connected. So you are so why is it three? So if we remove any two edges, this graph is remaining connected, right?
Yes.
Okay. So you can see if we remove any two edges, this graph is remaining connected. So first of all, if we are removing, if we so these three edges are basically the edges which are joining these two components. So if we just remove any two of these edges, if we remove any two of these edges, then also we see that we have a connection from this component to this component. So removal of two edges, and if we are removing some two edges from this a vertices from a b c e, then also this graph is not becoming disconnected. So we see that removing, if we remove any two edges, this graph is not becoming disconnected.
Disconnect.
So therefore G is three edge connected. But is G four edge connected?
No, it is not 4 edge connected because on removal of 3 edges, the graph become disconnected.
Yes. So if and what are those three edges?
That is DG, DJ, and CJ.
Yes. So if we take CJ, oh sorry, DJ, and EJ. So G minus S is disconnected. So we see that G is not 4 edge connected. So what is the edge connectivity then?
3.
Yes. So we see that k edge connectivity is 3. So is vertex connectivity and edge connectivity, definition of vertex connectivity and edge connectivity clear for everyone?
Yes.
Yes, ma'am.
Okay.
Yes, ma'am. So basically, ma'am, for
Yes.
every path, edge connectivity will always be one, no?
For every,
Path,
oh, you are saying for every. So
any path.
if a graph is just
Just
a path,
yeah,
so if graph is just a path, yes, edge,
edge connectivity will be one.
even the vertex connectivity will be one. If it
No, two connected.
no, so see, you are taking this as your G.
Vertex connectivity is one. Yeah.
If a, and so basically a path with more than two vertices. Okay, no, even that is fine. So we see that, yeah, for a path both kg and kg dash will be 1, k dash g will be 1. And you can, okay, so this was a path.
For a tree, ma'am.
Yeah, so if you consider a tree, so we have kg is, so we have, so if you consider some tree, yeah, so basically, so first we need, so if we are considering a tree, then removal is removal of one vertex making that tree disconnected. Yes, it will be, yeah, for tree also vertex connectivity will be 1. For tree also vertex connectivity will be 1. Because see,
No, ma'am.
for
Not necessary. Not
why,
necessary, ma'am.
why, okay,
Because you, if you remove one vertex,
yeah,
then
then
graph doesn't uh, disconnected.
graph will become disconnected.
No.
So,
In this example of what you have given,
hmm,
if you remove that top vertex,
yes, yes. So see,
then it is not disconnected.
yeah,
If you remove D,
yeah, but we have to ensure that for every vertex, right? So if we are say, so removal of D won't make this graph
any
disconnected, but removal of some vertex will sure make
okay,
this graph disconnected. So if
any
you
vertex, okay,
yeah, so see, in a tree there are so whatever what the vertex that you have put out is leaf. So if you take any non, if you remove any non-leaf vertex, then the graph will become disconnected.
okay,
So therefore
got
you'll see for for tree also vertex connectivity will be 1.
okay,
And if vertex connectivity is 1, then edge connectivity will also be 1. Because we have that vertex connectivity is less than equal to edge connectivity. So for tree, both vertex connectivity and edge connectivity will be 1.
So we can conclude that a graph having a breach will always have edge connectivity one.
Yes, 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 that is right. Because, so basically you are saying graph with cut edge basically, right? Graph with connected graph with a bridge is one has connected edge connectivity 1.
Ma'am,
Yeah,
uh, there is no cycle in the tree. So it
Yes.
is obviously no two edge connectivity.
Yeah. Yes.
So
Yes.
it's obviously one edge connectivity, and so one connected graph,
Yeah. Yeah.
one vertex connected graph.
Yes. Yes. You can give that argument also. That argument is also right. Yeah. So so what is he saying? So we have an equivalent definition of two edge connectivity from the previous exercise only. Two edge connectivity is same as saying that every edge should lies on a cycle. But in a tree there are no cycle. Therefore edge connectivity has to be so it cannot be two edge connected. Therefore edge connectivity has to be one, and therefore vertex connectivity is also one. Yeah, that argument is also correct. And this is true, this is by definition only. Your next question, that connected graph with a bridge has edge connectivity 1, because see, if it has a bridge, that means removal of that bridge is making that graph disconnected. So this, if it has a bridge, then that graph cannot be two edge connected, and therefore it has edge connectivity 1. So is this fine? Yeah. Okay. Okay.
Hmm.
I will. Yeah. Yeah. Now next question, this is also the question from one of the assignment. So in a simple graph with n vertices, if a minimum degree is greater than equal to n minus 2, then you have to show that uh, the edge connectivity is same as the minimum, vertex connectivity is same as the minimum degree. So this was this was one of the question in assignment. So see, so this graph, it is a simple graph with n vertices, and del g is greater than equal to n minus 2. So there are only two cases possible. First is that del g is equal to n minus 1, and second case is del g is equal to n minus 2. So if del g is equal to n minus 1, can we say anything about the graph? G is a simple graph.
G is complete graph.
Yeah, G is simple graph with n vertices, and del G is equal to n minus 1. So that means each degree is greater than equal to n minus 1, and therefore G is equal to Kn. And what was the connectivity of complete graph? We have shown previously only
n minus 1.
n minus 1. So for case 1 this is true, that del G is equal to Kg. Now what about the second case? Case 2 is when del G is equal to n minus 2. So basically suppose minimum degree is n minus 2. That means there exists a vertex of degree n minus 2. Say V1. So we have a vertex of degree n minus 2. So V2, V3 and Vn minus 1. So V1 has degree this, and then we have V, then we also have one vertex which is not attached to V1, and there can be more edges, but there is V1 Vn is not an edge for sure, but there can be more so there are more edges between V2 between these V2 Vn minus 1 and Vn, but there is no edge between V1 and Vn. Also, yeah, degree minimum degree is n minus 2. So these are n minus 2 vertices, and v1 is not attached to v1, so vn will also be having these connected to these. Okay, now we have to show that vertex connect. So we have this graph and there can be more edges, but all those more edges will be between this S. All more edges are within this S. There we have drawn all possible edges from V1 and all possible edges from Vn, and all the other edges are here. Now can you see that this graph will be the minimum size. So these are the minimum vertices that are required to disconnect the graph. That is, if we remove less than n minus 2 vertices, if we remove less than n minus 2 vertices, G remains connected. Can you see that? So see, if first of all, so suppose s so suppose we are so we have to show that uh, G, if we show that okay, so basically we have to show that if we remove any n minus 3 vertices, this graph is remaining connected. So if we, so these are n minus 2 vertices. So if we remove n minus 3 vertices, that so case 1 is all those n minus 3 vertices are coming from this set S. Case, so W has n minus 3 vertices, case 1, and we have to show that G minus W is connected. If we show this, then we have shown that this graph has connectivity n minus 2. So now if we, first case 1 is all these vertices are coming from S. If all these vertices are coming from S, since V1 is attached to all those vertices and Vn is also attached to this vertices, so we see that this graph is remaining connected because all vertices, so we have V1 and Vn. And on in the other cases also, so if we are removing n minus 3 vertices, there are some vertices remaining in some set S, and if there are some vertices remaining in some set S, then since V1 is connected to all the vertices and Vn is connected to all these vertices, this graph is remaining connected. Therefore we see that if we remove n minus 3 vertices, this graph is connected, and therefore since G is n minus 3 connected, but removal of these two vertices is making this graph disconnect. G is n minus 3 connected, but G is not n minus 2 connected. Sorry, G is n minus 2 connected, but G is not n minus 1 connected, because removal of n minus 2 minus 1 vertices is making this graph connected. So we see that connectivity of this graph is coming out to be n minus 2, because G is n minus 2 connected, but G is not n minus 1 connected. So is this fine?
Yes, ma'am.
Okay. Is this okay? So this was all on connectivity. Now there's just, since we have some time left, I'll discuss one or two things about network also. So first of all, what is a network? Network is a so now all, previously all those graphs that we have worked with were undirected. They were undirected in the sense that all there was no direction attached to any edges. So what is, first of all, what is a network? Network is a directed graph. That means every edge has a direction associated to it. It has two distinguished vertices, source and sink. So we have two vertices, source and sink, and every every edge is also assigned some capacity. So network has three properties. Network has three properties. It is a directed graph. It has two distinguished vertices, which is source and sink, and to each edge we have a capacity attached to it. So this is what is called a network. Now, what is a flow? So suppose this is, so basically this is a network. So this is a simplest network, ST31. Yeah. So what? Mhm. So a network has three property. First of all it is a directed graph. That means all the vertices have some directions. All the vertices have some direction. Then it has two distinguished vertices, source and sink. Source and sink, that is all the if it is source and source, by source vertex we mean all the edges are going out of source, and sink, all the edges are coming into sink. So it has two distinguished vertices, and moreover, so moreover, all edges have some capacity. Say, so this is an example of a network. Now, what is a flow? Now, flow is basically, you are given this network. You are given this network, which is a directed graph, and it has some. Uh, uh, this is there a question? Okay. So yeah. So the so this is a network. Now, what is a flow? Flow is basically, you are it is a function from v cross v to r. So it's v cross v to r. So you are assigning you are so you are assigning some integer to each edge. To each edge you are assigning some integer, and it should satisfy these three property. First is capacity rule. Flow of uv should be less than equal to capacity. So base Second is skew symmetry, that is a flow of uv is minus of flow vu. And the third is conservation law, that is if we pick any vertex other than source and sink, if we pick any vertex other than source and sink, the amount of flow coming into that vertex should be equal to amount of flow going out of the vertex. So the flow has these three properties. So any function which is assigning some real number to each edge, plus which is satisfying these three property, is a flow. Now, what is the value, and so once we know what is a flow, what is the value of flow? Value of flow is basically, you either compute all the flow going out of S, or you either or all the flow coming into T, and due to conservation law these two things turn out to be equal, and this is the value of flow. Now this is, once we know what is a flow and what is a network. Now, once we know what is a flow and what is network, then we want to solve this question. So we know that below graph has flow 2. Now we have to give directions so that conservation law is satisfied. Conservation law is, what is the conservation law? Conservation law is basically that any in total amount of inflow coming into vertex S should be equal, total amount of inflow into some vertex V should be equal to the total amount of outflow. So now we know that below graph has flow 2. Now S is our source vertex. So what do you think? What should be the direction of SA? Is it SA or AS? So below graph has flow 2, and flow is basically flow, value of flow is basically the total amount of flow which is coming into T or going out of S. So what is, do you think, is the direction of AS? Is it AS or SA?
SA.
SEM.
SA.
SA, because S is our source vertex, and since it has flow 2, so we see that it will have direction SA and SE. Now let's compute the now let's see what about AB. What is the direction of AB?
AB only.
AB only. Why? Because we have, so conservation law says that the inflow coming into A should be equal to the outflow going from A. So what is the inflow? Uh,
1.
what is the inflow in A?
1.
Yeah, inflow in A is 1, because what are the vertices coming into A? It is SA and DA. So we SA and DA, and the flow here is 1, here is 0. So inflow in A is 1 plus 0, 1. And what are the edges which are going out of A? They are AB and AC. Since AC has flow 0 and inflow should be equal to outflow, we see that AB should the direction of AB should be AB. Now similarly, what is the direction of CD?
CD only. CD.
CD. Yes, because inflow in C we see, again C is 1. So outflow should also be 1. So CD. And what about BT and DT?
DT. DT and BT.
BT and DT. Yes, because flow has value 2, so the inflow in T should be equal to 2, and this is the only inflow in T through BT and DT, therefore this is 2. So is the definition of network flow and conservation law uh, fine with everyone?
Yes.
Yes, ma'am.
Okay. Okay, now once we know what is a flow, uh, what is a network, what is flow, we want to see what we want to define residual network and augmenting path. So what is a residual network? So first of all, to define residual network is defined with respect to some flow. So we are given a network G and we are also given a flow F. Then residual network is a different directed graph which has same set of vertices as G, and it has one or two edges corresponding to each edge in G. So basically what is the residual network? So first of all, residual network is a graph. What are the vertices of that graph? Same as the vertices of G. But what are the edges of this graph? So we, if given a flow, following are the edges of the residual of the given a flow, following are the edges of the residual network. So first of all, if you are given a edge, if you are given a edge UV, if you are given a edge UV which has capacity 3 and flow 2, which has capacity 3 and flow 2. So in the residual graph, what will happen? So in the residual graph, what will happen, you'll draw two edges corresponding to this graph. You'll draw two edges from uv. So if it has so if the flow is strictly less than capacity, so you see in this case flow is strictly less than capacity and the difference is 1. So you'll draw a edge in the same direction with the difference, that is 1. And second condition is if flow is strictly positive, then you also draw an edge in opposite direction with the flow value. So in this case, this is the this. So if you have in your flow, in your network, if uv is an edge, uv is a directed edge with capacity 3 and flow 2. So corresponding to uv in the residual network, what you are doing, you are drawing an edge in uv direction whose new capacity will be the difference of this, so 3 minus 2. And if the capacity is strictly greater than if the capacity is strictly greater than sorry, if flow is strictly greater than 0, then you'll also have a edge in opposite direction with the flow value. So this is what we mean by residual network. So now I have defined residual network. Now we are this is the this
Ma'am,
is
how flow is greater than capacity?
sorry, huh?
You told you told flow is if flow is greater than capacity.
Flow, no, flow, sorry,
No, flow
I
cannot
flow
be
is
greater than
no,
capacity.
no, no, sorry, I meant flow is I meant flow is less than capacity. If flow
Yeah.
is strictly less than capacity, yeah. So now this is my network G, and this is the flow that I have assigned to this network. Now I want to draw a now with respect to this G and N, I want to draw a residual flow. Okay, so let's draw that. SAB. So residual flow, first of all, what are the vertices of residual flow? The vertices are same as the vertices of network. So which is SAB, C, D and T. Now what we have to do is, now we have to add edges. So corresponding to each edge we have to draw one or two edge. So first of all, if I am taking the edge SA, SA has flow 1, capacity 3. So first condition is satisfied, that is capacity is strictly greater than flow. So I'll draw an edge in direction SA with the value which is the difference of 2, which is 2. And also flow value is strictly greater than 0, which is 1. Therefore I'll also draw an edge in opposite direction, which is 1. Okay. Now what about AB? What all edges should be added in AB? What do you think? In the residual flow for AB, what all edges should be added?
Only backward edge will be there. Backward edge only.
Yes. So you see the
B
first,
to A. B to A.
B2A, because first condition is not sat flow, so flow is equal to the capacity, so we don't have a forward edge, but flow is strictly greater than 1. So flow is strictly greater than 0, therefore we'll have a backward edge. What about BT? What all edges will be there in BT in the residual flow?
Yes. For B to T is 2.
B2T is 2.
2. And T to B is 1.
Yes. T2B is 1.
T to B is 1.
So what about AD?
AD.
So first condition is satisfied. So for
Only
A,
forward.
yeah,
Only
only
forward
forward
edge.
one. Because first condition is satisfied, that flow is strictly greater than flow is strictly less than capacity. So first condition is satisfied. So we see there is a forward edge. But there is no backward edge because flow is not strictly great. Second condition is not satisfied. So second edge won't be there. And similarly, we can see this for same thing can be happen to AC and BD. So we'll have a DB with 2 and AC with 2, and there will be no second edge because
Forward is when forward is from D to A, no?
forward edge, okay, yeah, sorry, forward edge is from D to A, yeah, yeah, forward D. And similar, so see, in similarly AC and BD also have flow 0. Therefore we'll see that we'll only have edges in the same direction, and we don't have the edge in opposite direction. So AC will be there with capacity 2 and DB will be there with capacity 2. And what about SC then?
SC. Forward edge is 2 and backward edge is the 1.
Yes, forward edge is 2 and backward edge is 1. So basically the edge in opposite direction has weights equal to the flow, which is 1, and the uh, forward edge and the edge in the same direction has capacity, which is the difference. What about CD?
Only only backward edge.
Only
DC.
backward, because
DC.
capacity
1.
is equal to flow. Because capacity equal to flow, so first edge won't be there. That is, the edge in the same direction won't be there. We'll have an edge in opposite direction with the value of flow. And what about DT?
Forward edge is 2 and backward edge is 1.
Forward edges.
2. 2.
Okay, sorry, I heard this is black is for backward edge. Forward edges, back.
2.
This edge is 1,
Backward edge is 1.
yeah, and this is 2. This is for this 2. So now this is, and we have done it for all the edges. So is the definition of residual flow with respect to a flow clear to everyone? Like if you are given a network and if you are given a flow on it, if you have to draw a residual flow, is it clear to everyone how to draw that?
Yes.
Explain again, ma'am. Please.
Which part, like, yeah, so see, okay, uh, so residual, so basically you are given, so first of all you are given this network G. This is my network G, and this is my flow. So basically the the first value is flow value, and the second value is the capacity value. This is the notation. So first value is flow, the second is capacity. Now if you have to draw the residual flow, so what do you do? First of all, residual flow is a graph. Hello. Residual flow,
Hey.
residual flow is a graph. Residual flow is a graph which has vertices same as this. So basically now we are given this network and given this flow. Now we are constructing a residual flow, so the vertices will be same. So vertices are same, A, B, C, D, S, T. Now we look at each edge. Now is there any question? Now we look at each edge. If you have no question, please mute yourself. Yeah. So now it has vertices. Now it has vertices same as that graph G, and now corresponding to each edge in this graph you have to draw either one or two edges depending on the condition. So now you have this edge SA first of all. So you had this edge SA, it is 1 3. So flow of SA was 1 and capacity of SA was 3. So you see that flow is strictly less than capacity. Flow is strictly less than capacity. So you Sunil, can you please mute yourself? Yeah. So I was saying I was saying that, so now you have, now for each edge you have to draw one or two edges. So if you consider this SA edge, so this SA edge has 1 slash 3, that means flow is 1 and capacity is 3. So you see, first condition, that flow is strictly less than capacity, is satisfied. So you will draw an edge in the same direction SA with, and the new capacity will be the difference of this. 3 minus 1 is 2. Therefore this is one edge. And what is the other edge? If this flow is strictly greater than 0, then you draw an edge in different then you draw an edge in opposite directions with flow value. So you'll draw another edge AS with 1. Now you do, now for residue flow, this is just for SA. Now you do this for every edge S, every edge in G. And once you have done this for every edge in G, you get the residual flow diagram, residual flow graph. So this is how I did for SA. So now let's take one more example. So now if you take this edge DA, now if I take this edge DA, sorry, it is, yeah, DA. So DA has 0 slash 2. That means flow of DA is 0 and capacity of DA is 2. So first condition is satisfied, that flow is strictly less than capacity. Therefore, in the residual flow graph, you'll draw an edge DA. You'll draw an edge DA in the direction. So you have this DA whose capacity will be the difference, which is 2 minus 0. So therefore we have this edge dA with 2. Now the second condition is if flow is strictly greater than 0. But here you see that flow is 0. So the second condition is not satisfied. So second edge will not be there. And now if we consider again if we consider just the edge CD, it has 1 1. So CD has flow 1 and CD has capacity also 1. So here you see that first condition is not satisfied. First condition was that flow should be strictly less than capacity. But since here flow is equal to capacity, so first condition is not satisfied. So you won't have an edge in the direction of CD. But the second condition is satisfied, that the capacity is strictly greater than 0. Therefore, you'll have an edge in opposite direction, that is DC, with the flow value which is 1. Now this I have shown you for 3 edges. Now if you do this for every edge in this graph, for corresponding to every edge in this graph, you add 1 or 2 edge depending on these two conditions, then what you get is the residual flow. Now is it clear what is residual flow?
Yes, ma'am, got.
Got it.
Yes, ma'am. Clear, ma'am. Thank you.
Okay. Yeah. So this was the residual flow. And the last definition is just the definition of augmenting path. So here you see this is your flow this is your network and flow diagram. Now, this is the residual flow with respect to this graph. So basically what I have done this myself for this graph. So what I have done, so this was a flow diagram, and this was a, so we, like we did for previous example, we have constructed a residual flow graph. So what is the augmenting path? So now, once you have this residual flow, augmenting path is a path from sink to so sorry, from source to sink vertex in the residual flow diagram. So you so augmenting path is basically you want to go from S to T in the directions as the direction suggested in the directed graph. So any directed path from S to T in residual flow graph is your augmenting path. So in this case, you see, if this is my residual flow diagram, augmenting path will be SA, AC, CB, BD, DE, and ET. So any directed path from S to T is the residual, is the augmenting path. Any path from S to T in residual network is your augmenting path. So now is the definition of so this was what I wanted to discuss for the networks and flow. Basically the definition of flow, definition of residual network, and definition of augmenting path. So are these three definition clear to everyone?
Yes, ma'am. Clear, ma'am.
Okay, so this was all for today. So if you have any questions, you can ask.
Ma'am,
Yeah.
ma'am, I have a question from week 5. Can I ask now?
Yes, yeah.
Ma'am, I have doubt in the Peterson theorem.
uh, Peterson theorem, what was the theorem? Yeah.
It says that if G is bridgeless, three regular graph, then it has a perfect matching.
Okay.
I want to ask that if the graph is not bridgeless, then can we say that it may or may not have perfect matching?
Okay, first of all, you are saying that if G is bridgeless,
If G is bridgeless, three regular graph, then it has a perfect matching.
if G is bridgeless, 3 regular, then G has perfect matching. Okay.
Yes, this is the Peterson theorem.
Okay. And what is your doubt?
I want to ask that if the graph is not bridgeless, then can we say that it may or may not have perfect matching or it will not have perfect matching? Like, is it a necessary condition?
No, that is not a necessary like, no. So if you are saying if G, so you are so if G is, you are saying if G is not bridgeless, right?
Yes, ma'am.
No. So you can't, no, if G is not bridgeless, then you cannot conclude anything about perfect matching or not.
Ma'am, actually, in the lectures, we have Sylvester graph in which
Yeah.
it is a three regular graph and it was not bridgeless.
Okay.
So
Yeah.
did we conclude from this theorem that it does not have a perfect matching, or we need to draw and then check that it does not have a perfect
So you
matching?
had the Sylvester graph, which was 3 regular.
Yes, ma'am.
Yes.
And it was not bridgeless.
And it was not bridgeless. Yeah.
And it did not have perfect matching.
Okay.
But in assignment 1, question number 1, in
Yes,
assignment 5.
but you cannot, yeah, no. So you cannot conclude this from that theorem.
Okay, ma'am.
So
Okay.
this theorem is just saying that if G is bridgeless and 3 regular, then G has a perfect matching. But it is
Okay,
not
ma'am.
saying that if G is 3 regular and not bridgeless, then G won't have a perfect matching. This is not true.
Okay, ma'am. So for this Sylvester graph, we need to apply some other method to conclude that it does not have a perfect matching.
Yes.
Okay, ma'am. Okay. Thank you so
Okay.
much, ma'am.
Okay. Yes. Any?
Ma'am, the path capacity,
Yeah.
you didn't explain about that, I think, ma'am.
Oh, yes. Okay. Oh, so path capacity is basically this. So when once we have found the augmenting path, so this is the augmenting path, right?
Yes, ma'am.
So augmenting path is SA, AC, CB, BD, DE, and ET. And now you write down the capacity for each graph, for each edge. So it is 2, 2, 1, uh, for BD it is 4, for DE is 2, and for ET is 3. So basically path capacity is minimum of capacity of edges. So you look at all the edges in that augmenting path, and the minimum capacity and you come the minimum capacity from all the edges in that path is the path capacity. So here you see the minimum number is 1, therefore path capacity of this graph is 1. So path capacity is just the, once you have found the augmenting path capacity is the minimum capacity of all the edges in P.
Okay, ma'am. Yes, clear, ma'am.
Okay. Yeah. Any other question? Okay, then I'll see you next time. Okay.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Yes, yes.